Good morning, everyone. Are you all able to hear me? And a poll question to check this. Are you all able to hear me? Yes or a no? Uh, what did I just do? Okay, wonderful. 97% of you all are able to hear me. That's a good thing. And you also are responding over the chat window. Okay, as usual, we shall get started with a quick recap and then we shall proceed further. Okay, so let me unshare and share the entire screen and we shall go to the mind map. Within the mind map, thanks to our expert Shubha, I think we are able to, you know, able to get things in a right way. I think there are still a few things that have to be updated. We shall update it slowly and steadily. And hmm, I think this is yet to be updated. We shall update it. Okay, let's look at this. Let me also make a note. One second. AI update. Okay, done. I'll get this updated. All right, just give me a minute. Just give me a minute, sorry. Sorry about that. So I'm having this specific mind map updated here, the latest version, so that you might have access to the latest version. Once again, just to do a quick recap, we started off by discussing about project management methodology, which is CRISP DM, cross industry standard process for data mining. And we understood the business problem. Once you understand the business problem, you need to record the business objectives and business constraints. Once you're done with this, we proceed further with data collection because we all are AI experts and we need data, right? To be able to analyze data and take data driven decisions. For that, we discussed about the various data types. We discussed about what do we mean by continuous data, discrete data, qualitative, quantitative, structured, unstructured, big data, not big data, so on and so forth. Once you're done with the data types, then you proceed further with data cleansing or data preparation, exploratory data analysis, or feature engineering. Once you perform all of these activities, then you proceed further with data mining or machine learning. Within this, we just discussed about artificial neural network or multi-layered perceptron. And once you build your model, you evaluate your model. This is also something that we have done. And finally, you deploy your model. For deploying, you need to understand what resources are required, what servers are needed, what hardware, what software is needed. Then you need to plan for regular monitoring and maintenance. When do you monitor? When do you update your model? Right? And you devise your strategies to retire, replace, or update your model. I mean, you build a model and it would be applicable for the rest of your world, right? Rest of the time. It doesn't work that way. A classic example is COVID 19. Whatever models have been built before COVID 19 have to be updated now because this is post COVID 19. Scenarios have changed. The way people behave, the way people react, all these things have changed significantly. So this is how it works. And then, um, yep, let us now get into, okay, one more thing. We also discussed about mathematical foundations within which we discussed about optimization. Then we have deep learning primer, wherein we discussed about what do you mean by compositionality, right? What are the initial hidden layers? What will they capture? What will the next set of hidden layers capture? What will be the final set of hidden layers? What do you mean by perceptron algorithm? Artificial neural network? What is multi-layered perceptron? All these things we have discussed. We have also looked into this Excel sheet wherein we documented information such as if output variable is continuous, you'll have one neuron in your output layer. Then if activation, what is the activation function that we use in the output layer? It's linear or identity output layer. And the loss function that we use is mean error or mean squared error or mean absolute error or root mean squared error, mean percentage error, mean absolute percentage error. You can use any of those. If your output variable is continuous, your loss function and error function would be the same. Okay, and we also know that loss function is for a single row and cost function is for all the rows put together. If your output variable is discrete in two categories, then you can either have one neuron or two neurons. And then you'll have sigmoid. Sigmoid is an activation function. A few people also use tanh, hyperbolic tangent. And you use binary cross entropy for loss function or cost function. And then to evaluate your model, you use confusion matrix or cross table. If the discrete variable has more than two categories, like for example, say you have 10 class classification problem, then you'll have 10 neurons in your output layer. Then you'll have softmax, which is going to be your activation function. Then you'll have loss function or cost function, which is categorical cross entropy. And then you have confusion matrix. And we will get back to this yet again when we discuss about convolution neural network. Today, we are going to spend our time on um, a lot of other algorithms and computer vision and image processing. So let's get there. And let us get started with computer vision. Computer vision and image processing. Majorly, we are going to use OpenCV, Open Computer Vision, to be able to handle the image related problems. Here is a vision related problem. Question to you all. What do you see here? What is there in this image? What do you think exists in this image? Yep. What is there in this image, friends? And if you give this to humans, and if you ask humans to actually look at this image and determine what is there in the image, then you might be confused on what is actually there in this. But then, if you look at it, now you understand that there is a cow. These kind of scenarios where humans cannot effectively identify on what is there in the image, computers can do a better job. Computers can do a better job here. If you look at this specific image, what is there in this? Anyone? Any thoughts? What do you think this is? Can you all guess on what is there? You have a board, whiteboard with a marker and papers, etc. For humans, it might be very difficult to identify what is there in the image. But then, if you supply a similar kind of image to your computer will do wonders. Okay, for example, this is another scenario where your computers might do a good job. So here, by looking at this image, in the world that we live in now, we can actually give a caption to this image. And the caption could be, seems like this is a train engine which rammed through your wall and it came down falling on the street. Your computer can actually give a caption to these images. What is there in this image? You know for a fact that there are 4 people, there could be a US flag, maybe, so on and so forth. Maybe 3 are men and 1 is woman. Okay, it might be slightly difficult for us, but computers can handle it. Recognizing the objects, recognizing the pedestrians. All these are a few of the use cases which are already solved, right? And now world is working on 3D images. How do I analyze a 3D image? And this is what people are working on. There are a lot of problems that can be solved by using your image processing and video analytics. And the kind of problems that can be solved is a verification problem. Do we have a lamp here in this image? Is there any lamp? Or if your question is that a lamp? Your system will detect, your computer will detect and respond back to you. You can ask questions such as, where are the people? Then your system or your chat bot or your computer would respond back saying that, hey, this seems like a outdoor scene wherein people are shopping. Pose estimation. What are people doing? What pose do they have? They're all walking, or majority of them are walking. Activity classification. What are they doing? They're just relaxing or shopping or doing something else. Okay, object categorization. What kind of an object is this? You can ask those kind of questions. Scene categorization. Is this indoor, outdoor, mountainous region, so on and so forth. Attribute recognition, right? What are the various attributes of the object in the scene? You have trees, you have a flag, you have shops, right? All these kind of problems can be solved using simple image processing and video analytics. If you observe this, say you have taken an image of this and you want to know on what is there on the other side. Okay, you want to know on what is there on the other side. But you don't know because this is obstructing your view. This building is obstructing, or the roof is obstructing your view. If you can give this to your computer vision application or convolution neural network, and if it gets trained on a lot of such images, it would actually do this kind of a mapping and give you an output. And you know exactly on what is there on the other side. It will look at all the historical images that you have supplied, and it is going to logically pick up those parts of the image from the other images which might make sense, and it's going to display like this. Wonderful. In a lot of other places also, we have computer vision being used heavily. For example, you have driverless vehicles wherein you have a stereo camera. Stereo camera has two cameras basically. You'll have two cameras, and then it will also identify the depth, how far or how close you are. Then these kind of applications existed since long, wherein you just go to any monument, you open your application, you scan it, scan the image, it would automatically go connect to your Wikipedia or some other forum, and then it's going to respond back. You also have Mars rover, wherein Mars rover explores planet Mars, and it gives the information, okay, about the planet Mars, images, videos, and all that. You can also look at Google product search, wherein say you have a product, but you don't know the name of that product. So simply you can take the image of that product and upload, and it's going to respond back. And you also have a lot of image recognition, number plate recognition. On checkbook, determining what numbers are written here, right? Playing some kind of Sudoku, etc. Looking at your fingerprint impression and looking at the various contours to determine whether it is you or not. We have a lot of facial recognition applications wherein it scans your face and determines on what is your age, what is your gender, so on and so forth. This is face recognition. We will build face recognition system. We will do it in Python using OpenCV. We have done a project in Malaysia wherein we were supposed to keep monitoring the parking lots, and we had to update the information in the backend application, mobile application, on how many slots are empty. Okay, we had to do that. If any of these slots is empty, then immediately it gets updated on your mobile application, and the person who has access to this receives a notification. If you're closer to that location, that area, then it gives you notification saying that, hey, in this parking lot, in this parking bay, there is one parking lot which is available. You can go park your vehicle there and job done. In driverless vehicles, we have lane recognition. It will recognize the lane. During nights, it might become tough for the driver. And you know what? It also does prediction. Autonomous trucks, like you have your autonomous cars, you have autonomous trucks, meaning driverless vehicles. So if you're traveling in this way, if there is a hairpin bend or a bend here, right? Hairpin bend, which is available here, which exists here, then if you're here, your model also predicts on what might be on the other side, predicting based on a lot of videos which have been captured in this location. It can predict that, okay, if this is an accident prone area, then I'm sure there might be vehicles coming on the wrong side also. How do we counter that? If you take an image and if it's so bright that your face is not clear, automatically adjustment happens. This is another example of image processing. If you smile, immediately of your cam recognizes you and takes a photo. This has been there since long, right? These are all applications of computer vision. We all are cricket fans, right? So do you see the Hawkeye? Okay, and all these things that you see are applications of computer vision. You must be seeing in your sports, right? People do such marking and say, okay, this guy, if he goes there, I think it'll be better. This guy should have moved there. Your one thing is your commentators do this. Another thing is your coach, right? In a lot of American rugby, etc., they do this. And also in Olympics, you would have seen that in the lane that people swim, they overlay the flag. Okay, they overlay the flag on top of the lane. This is also a classic example of how we can use computer vision. Then we have Microsoft Kinect. Kinect is going to help you play a lot of games, right? It has a stereo camera, meaning it will have two cameras. One will capture the image, one will capture the depth. Depth means how far or how close you are. If you're playing here, say you want to play golf. If you go to a golf course, it's going to cost you a lot. Okay, it's going to be costly affair. So what you do is you will play golf. But then even before you learn golf, if you go to golf course and say I want to learn, it will be a little costly. So what you instead do is you stand in front of this Kinect and then You keep swinging your golf club. Like we have bat in cricket, we have golf clubs, right? You keep swinging. Based on the kind of swing that you do, whether you're swinging it straight or is your bat going cross, what is the speed at which you're swinging, it will display here on where the ball would eventually go and land up. Okay. But there are a lot of challenges also. For example, there is a lot of intra-class variation, meaning, say you want to recognize chair and you're building a model such that if there is any new image, it will classify on whether it is a chair or not. When you supply all the chairs for this particular chair, it might be very difficult to determine that this is chair. It appears as if it is something else. It doesn't appear like a chair at all. Also, we have something called as viewpoint variation, meaning if you take a side view or a front view or a top view, no matter what view you take, your image has to classify that this is a dog. In certain cases, it cannot, it might not identify, but how do we counter this? We will learn. There are a lot of data augmentation techniques we'll learn. Illumination effect. If any of the image is bright and if any of your images is dark, right? Your system should be able to recognize that this guy is, I don't know, Lee, whether this person enters during a sunny day to office or during a cloudy day to office where the lighting is not good, your system should still recognize. That's the beauty of automatic attendance tracking system. And you have a lot of background clutter, right? For example, where's Waldo? Finding Waldo problem is what they call this as. We'll look into this also, yeah. There might be a lot of background clutter and maybe Waldo is lost in the crowd at a beach. Then how do you recognize on where is Waldo? Yeah, very difficult, right? But then if you supply this Waldo's image, this guy's name is Waldo. If you supply Waldo's name or image to the computer, and if you supply this image which was taken on a beach, it would do a quick image comparison and then give out the result. Okay, then we have occlusion. When one puppy might be hidden behind another, one might be hidden another. So it is very difficult to count on how many puppies are there here. Yeah, it's going to be a very difficult affair. This is called as pose deformation. It's not occlusion, pose deformation. Meaning, okay, you can recognize this is a dog. This also with difficulty, maybe your system would say this is a dog. But here there'll be certainly a challenge. Because at one specific point, it appears as if it's a human running. So these kind of issues also arise. And finally, the final challenge is that when it comes to images, there are hundreds and thousands of different categories. If an image is given, how do we actually recognize that that image is a specific image that we are interested in? Yeah. So all these things and many more we are going to discuss today and also in the next sessions to come in. We will spend some good amount of time on computer vision. Yeah. First of all, let us get started from the basics on what is an image. I'm sure you all know what is an image. You might say that, hey, we know that. But then a few basics. Whenever there is illumination or energy source, if it falls on an object, that object will appear to us as an image. Say you're staying in a room, you switched off the light, and there is no energy, there is no light. Then can you see the objects? No, you cannot. Only if there is a light which falls on an object, it reflects back, and just because of that reason, we are seeing what we are seeing. Otherwise, you would not see anything. And once you get an image can be broken down into multiple pixels. All these are various pixels that you have. And first, let us discuss about grayscale image. On a grayscale image, it ranges from 0 to 255. 0 means black, 255 means white. Okay, 0 means black, 255 means white. Okay, this is one thing that you need to remember. What happens if it's a color scale image? We will discuss. We'll practically also learn that. Okay, so this is white, so the corresponding number is 255. This is white, so the corresponding number is 255, so on and so forth. If you look at this is pitch dark, completely black. So you get 0. 0 means black. And this number which is to the left here, that is also black, but not as black as this cell. This is black, no doubt, but it is not as black as this. So it won't be 0, but it will be a number which is close to 0, which is 20. And then if you observe here, you have 47. Okay, this is the number, which is not completely black, neither is it completely white. It is somewhere in between, a gray color, but it is closer to dark. So it has a number which is closer to 0. And if you observe this, which row? 1, 2, 3, 4, 5, 6, 7, 8, 9. Ninth row, 1, 2, 3, 1, 2, 3, 4, 5, 6. So somewhere here, maybe this part, this one is what we are talking about, maybe, right? So 200. It is not white, but it is close to white because it's very light gray color. So it'll be closer to this. This is how you first take the values and put it here, and handling pixel intensity values is the most basic thing, and these pixel intensity values are called as the raw features. The most raw feature that you can extract from an image is the pixel intensity value. The most raw feature that you can extract from an image is your pixel intensity value. Simple. Okay, now, so you have an image which is in unstructured format, and then you're converting that to a structured format. Okay, and each of these pixel values can go into an Excel sheet as a column. So this will be the first pixel value. This is a second pixel value. This is a third pixel value, so on and so forth. Simple. I had an unstructured data set, which is an image. You converted that to a structured format into a table. Next, image that you have we will do all these things in Python. Practically, we will take the images and we will do it, okay? But then you will have to understand the basics first, and only then when I use the computer to build facial recognition system, you'll appreciate it. Otherwise, you'll not understand. Yeah, that is one thing that you need to remember. Here we have an image of Arnold Schwarzenegger, right? Austrian Hulk. Okay. Now, of course, American, Austrian American. So you have an image from Terminator movie, and you have x-axis here, and you have y-axis. Okay, so you're plotting x and y. Think about you tilting this x and y. You're just tilting it this way, and you're putting it like this, y. You tilted this image like this. You're making this image sleep on this surface, right? This is how it would appear. When will it appear like this? When on this axis you have the intensity values, pixel intensity values. So you look at all the regions. For example, if you look at this part until here, this complete part and this part is very black, dark. So it will have values zeros, right? If you take pixel intensity values, it ranges from 0 to all this 50, 100 and all that, assume, to 255. Wherever you have a black, there'll be a valley, deep valley. It will be here. And wherever you have slight gray color, it'll be slightly higher. And if you look at this portion, this patch, it's completely white. So when you look at that patch, it will have a peak. Why peak? Because 255 is white, right? And it's here. And then again, after this, you see how it's appearing, right? Look at this on how it's appearing. So there is a valley once again, right? Again, here, if you see, there is a peak. Here, there is a valley. Okay, so what I mean to say is, if you have an image, this specific image can be represented as a function. It can be represented as a function. If you take a color image, such as RGB color space, okay, if you have a color image can be split into multiple channels. Okay, this can be split into multiple channels. And you have a red channel here. Here you have a green channel. And here you have a blue channel. You have three different channels: red channel, green channel, and blue channel. And if you take each individual channel, it once again appears as if it is a grayscale image, black and white image, right? So a color image is nothing but multiple gray images in some sense. And when you combine all these, once again, you'll get back your color image. So when I say we are dealing with images, be it color image or grayscale image, it doesn't matter, because at the end of the day, Color image is nothing but combination of multiple grayscale images. That's it. Let's take this image and do a few elementary transformations. Say you have this image. Not, sorry, this is an output, okay? Say this is the image that you have, input image. F of xy means what? Pixel intensity value. You'll have x-axis and y-axis. At each point, you'll have some pixel number, pixel value. That pixel value ranges from 0 to 255. We all know that. And we also know that 0 means black, 255 means white. So if I say f of 1 comma 1, that means you're referring to this. This is if this is 1 and this is 1, right? And then f of 1 comma 2 would be this. So in that way, f of x comma y would keep giving you the pixel intensity values for each and every pixel that you see. Now my question to you all is, if I take each and every pixel value and if we add 20 to it, okay, you take each and every pixel value, intensity value, which ranges from 0 to 255, and if you add 20 to it, what do you think will happen? Yep. What do you think will happen? Let's see. Let's see how many of y'all will get it right. Please respond. I request everyone to please respond. Okay. Wonderful. So here, if you take each pixel value and keep adding 20, for example, you have a black color here, dead black, means it will have a value 0. If you keep adding 20 to it, for each and every value, you are making your image move towards this white zone, right? You're adding to all these pixel values, you keep adding 20, and then it will keep moving towards white. If the value is 255 already, for example, this patch will have 255, and if you add 20, it will become 275. But then you clip it. You clip it back to 255 because this is the maximum value which you can get. Okay, this is the maximum number that you can get. So your image becomes brighter if you add pixels to it, intensity values, if you add numbers to it. Then another question. Let's see how many of y'all will get it right. These are very basics, but if you get it right, I'm sure computer vision will be like the back of your hand. Okay, I'm taking an image. Again, once again, you'll have x-axis and you'll have y-axis. And then if I flip the x-axis, what do you think will happen to your output image? This is your input image and this is your output image. If I take minus x, then what do you think happens to this? Think and answer. There's no hurry. And I can also give you a shortcut or a hint, a pointer. We all are aware of the graph books, right? Let me show you the graph book once. So the graph book is going to be like this. These are all the graph books. I'm sure we all have worked on graph books when we were kids. Green color, blue color, pink color, many different orange color, many types of books is what you'll have. On on those books, what we used to do is we used to take the origin and we used to have x and y axis. On x axis we used to have positive numbers 1, 2, 3, 4, 5 in that way, and on this side you would have negative values -1, -2, -3, -4 in that way. Here you'll have again positive numbers 1, 2, 3, etc. And here you'll have negative numbers -1, -2, etc. Okay, and if you have an image like this, okay, x and y, all you're saying is let the y be like that, but for x I will take a minus, meaning for all of these 4 take a -4, 3 in that way. Then what happens to your image? Your image would get flipped like this. Okay, imagine you're holding here and then it's like a book page. This center, this is a book page. If you turn it like this, image will be flipped. So this portion will come on that side, this portion will come here. So your image would actually get flipped. Okay, next. There are a lot of image related operations such as point operation. You'll have local operation and you'll have global operation. Let's understand point operation. Point operation means in your entire image, take each and every pixel, each and every value, and do something with that. For example, here what we have done is we have taken each pixel value and we have added 20 to it. This is called as point operation, right? This is called as point operation, wherein you take each value, add something to it, and you get an output. Okay, next. You do a local operation. Local operation means you take a point, right, a single point. Rather than taking only this point into consideration, what we do is we're going to take all the pixels around that and use all these values also to get the new value for this. Okay, for example, if this is your image and you took a patch here and you have the output image. Okay, and say you have a patch here. Then you take each pixel, do something with it. I mean, add 20 or so, and then you get the output. That's what we discussed. Take this pixel, add 20 to it, and you'll get this. This is what we discussed, right? But then what I'm saying is that is point operation. If you're speaking about local operation, you take this point and you take the values around that. You take the values around that, and then you use even these values around this to get a new number, and this will be your new number. Okay, so you take a number, you take the values around this, and then you get a new number here or a new value. Okay, so when you take the local neighborhood, it's called as local operation. Next, we have a global operation. Global means you take all the pixel values, and then maybe you might want to add all these pixel values or do some other operation with that. And if you want this pixel value, you take all the pixel values and then combine them and get a new value here. That's called as global operation. Not often you use this, but if you just want to apply a scenario wherein given an image, is it an indoor scene or is this an outdoor scene? Okay, a specific image, is it an indoor scene or an outdoor scene? To identify this, we need to apply global operation. Global operation means take all the values and do some operation with the, and then you get the value here. Simple. Okay, now there is also something called as reversing the contrast, meaning wherever you have white, make it black. Wherever you have black, make it white. That's called as reversing the contrast. Okay, you apply such an operation. Don't worry too much about this. Okay, don't worry too much about this. You're just saying that new pixel value here will be old pixel value, subtract the maximum value, take the maximum value which is in this image, say maximum value is 200. Say you do not have any white spot at all. Your values range from 0 to 255, right? Say the maximum brightness that you see here is 200. So you said 200 minus each and every pixel value plus the minimum value. That would give you a new pixel. This would reverse the contrast. If you don't understand this, don't worry, forget it for now. I mean, you just assume that there are certain operations. So we have contrast stretching, meaning you just get hold of the contrast and stretch it. Okay, this is called as contrast stretching. Okay, once again, when you do contrast stretching, what you do is you apply something called as histogram equalization or histogram stretching. What does this mean? Histogram, the basic idea you should be aware of is that it will group the entries together and give you such a histogram. Say you have numbers from 50 to 100, 100 to 150, 150 to 200, 200 to 250, so on and so forth. When I say histogram stretching or equalization, what you do is you take this 50 to 100 and then you're going to break it down into finer branches. So what you'll do is 50 to 100, you're going to split them into 50 to 60, and then you'll say 60 to 70, then you'll say 70 to 80, so on and so forth. So 50 to 60, 60 to 70, 70 to 80, so on and so forth. So this will become one. Then you'll have 70 to 80 to 90, 90 to 100 in that way. So what you're trying to do is you're trying to break it down further. And when you break it down further, this is how it's going to be. Okay, then this is called as histogram stretching. Okay, and a question that I have. Say I give you a camera to capture an image and I make someone stand still. Okay, and then how can you reduce the noise using point operations? I'll give you a beautiful image of a beautiful person, right? Then all I'm going to say is if you take one image of whom should I take? I mean, let's take Sushmita Sen, okay? And then I give you a camera. You take a photo. You get this. But then I would say that, hey, do you know what? On this image, there are that white spots, gray spots, black spots in that way. That means all these spots that you have is called as noise. I would say, hey, man, there is no clarity. I mean, it's good, but all these spots I don't like. And I want you to remove those spots. And I say that you can do only a point operation and get rid of these. How would you do that? Please, can you answer? Let's see who will get it right. Please, I request everyone to resort to the chat window and respond. Anyone? Okay, so fine. So let's do this. Take a lot of images. Okay, take a lot of images. And if each of the image has some noise, when you take average of all of those, take all these three pixel values, take average of pixel values, and you'll get the final image pixel value here. Take the next pixel here, take here, take this, because you're taking multiple images. Say you took three images. Different images will have different pixel values because you're having some noise. So you take all these three, take an average of those, you get the next pixel. Now take the next pixel values, take an average of all these three, and then you get the next pixel value. Then take all these, and then take once again average of all these points, and then you get once again the pixel intensity values, so on and so forth. This will reduce the noise in your data. Okay. Um, so it's 11:30. A few of y'all were saying let's stick to the break time. So what we shall do is we'll quickly take a break and then we'll get back. Yep. So it's 11:30 now. Let us take break until 11:40 and let us be back.
Bernie, could you please check your audio once?
Oops. Okay. Yeah. Sorry, my bad. Oh, I covered a lot of ground. My bad. Okay. So let's repeat. Let me repeat the portion which I have covered. So I was saying that if you have multiple pixels, okay, multiple images rather, and if you have pixel values in this way, you take all those pixel values and take an average of those pixel values and you get a new value. Then you take all the other pixel values, take an average of those and you get a new pixel value. Take average of all these pixels and then you get a new pixel value. So on and so forth. But then that is called as point operation. Now we will look at local operation. Local operation means not just taking each and every value and doing some operation on that, but we are going to take neighboring values also. And we have something called as moving average. What happens in moving averages? Say you choose moving average of 5. You can give any number. It need not be 5. You can say 6, 7, 8, 9, 10, any number. I'm just for your explanation giving 5. When you say moving average of 5, what you are going to do is you'll take this pixel and you take 2 pixels towards the left, 2 pixels towards the right, and you take average of all these pixels. And when you take an average of all these pixels, you get this central pixel value. Okay, you get that central pixel value. This is moving average. And in that way, do this for all the pixels. Say you want a pixel value for this, what you do is you take 2 pixels on the left, 2 pixels on the right, you take all these pixels and then take an average, that would be this. So the beauty here is that the moment you perform such an operation, the resultant will be very smooth. And this example that I've given here is of one-dimensional signal. Your audio files or speech transcripts are of one-dimensional, right? They are one-dimensional in nature. If you look at images, images are two-dimensional. And here you have an input image and you have an output image. On the input, say your this is a two-dimensional, images are 2D. So what we are going to do here is, or what we are expected to do is, you have to give two values. Say you're taking a 3 by 3 window, means you'll take a 3 by 3 space like that, and you're going to apply that here. If you apply a 3 by 3 here, then you have all zeros, right? You have to take average of all these numbers. 0, 0, 0, 0, 0, 0. If you take average of all these numbers, you get a 0. That's going to be your central pixel. Now move this one stride at a time. When I say one stride, it is 1 pixel. Okay, you move it by 1 pixel towards the right, and you take all these values and take an average of all these values. When you take average of all these values, you get the value of the central pixel. That's here. Then once again move it one stride at a time. So it'll be here. Then take all these values and take average of all those values. That will be the central pixel value. Keep doing it throughout your image, and then ultimately you will get this as your output image. So you have your input image and then you have your output image. Okay, now this filter, I mean, whatever you're applying here, like this, a patch, a 3 by 3 moving window, is called as a filter or a kernel or mask. All mean the same. It is called as a filter or mask or kernel. Okay. So you take your input image, you take your filter or kernel or mask, and you apply that on your image. When you apply that on your image, you get an output. Okay, and then you get an output. So you take all these values, you apply this filter or kernel or mask on this, and you get an output. How? Let's see. You say 10 multiplied by 0 plus 5 multiplied by 0 plus 3 multiplied by 0 plus 4 multiplied by 0 plus 6 multiplied by 0.5. 6 multiplied by 0.5 will give you 3. 1 multiplied by 0 will be 0. 1 multiplied by 0 will be 0. 1 multiplied by 1 will be 1. 8 multiplied by 0.5 will be 4. When you add them, you get 8. But you're just going to get the value of the central pixel by taking help of the neighbors. This is called as local operation. Okay. This simplest of the kernel that you have seen here is called as linear filter. Now, question to you, let me see how many of y'all will get it right. Say I mark something here. Okay. What kind of filter do I need to apply? What filter values? Say I have a 3 by 3 filter. What should be the values of this filter such that I erase this? To erase this, what filter values should I use? Let me see how many of y'all are actually thinking analytically here. This will be a poll question coming your way. What pixel values do we need to apply in the filter, or we need to have in the filter such that we erase the mark? 255, all zeros. Yep. Please, can you answer this? I'm sure you all will get it right. I want to just erase this part, this red patch. And I say that I have a 3 by 3 filter. What should be the values of this filter for me to erase this? Okay. To answer that, you should be again aware of your pixel intensity values. When you look at your pixel intensity values, you know that 0 means black, 255 means white. And I want to erase this. To erase this, what pixel value will you use? White color, you want to erase this. So you want a white color filter, right? So for example, if I just go here and choose this eraser, this is an eraser that you're seeing, right? If I go and apply this eraser here, it should make this white color. It should make it white. So the values of the filter should be, in literal sense, the use of this eraser and the values this eraser is going to apply would be all 255 values in this way. See, it's erasing everything. It's erasing means it is applying a filter which has all 255 in it. That's it, simple. Okay. A few things I would be skipping, a few math part which is not that important. Okay, this I will discuss. Okay, there is an operation called as cross correlation. Say you have an input image. Okay, say you have an input image and say you have a filter. You take this filter, apply on this input image, and then you get an output. Okay, so you take this filter, you apply this filter throughout your input image, and then you get an output. Okay, and the properties of filter is that if you have all ones, 1 1 1 1 1 1 1 etc., in that way, when you add them up, summation of these weights should be equal to 1. Summation of all these weights that you're seeing should be equivalent to 1. But here, when you add all these numbers, you get 9. So you divide it by 9 to ensure that summation of weights is equal to 1. Okay, so this red color patch should be here actually. This red color patch should be here. And then you have this central pixel. You get this, right? So when you take all these values and when you take an average of all those values, you get the central pixel. So you're saying 0 multiplied by 1 plus 0 multiplied by 1 plus 0 multiplied by 1 plus 0 multiplied by 1, 0 multiplied by 1, 0 multiplied by 1. You'll get all zeros. Then 90 multiplied by 1 plus 90 multiplied by 1 plus 90 multiplied by 1, it will give you 90. When you add them up, you'll get 270, but it's again you multiply it with 1 by 9, which will give you 30. Okay, if you increase the size of your filter, you take a filter size, and if it is 3 by 3, it will have some blur. It will create some blur on your image. If you increase the filter size to 5 by 5, and if you apply on this, the amount of blur that you see will further increase, the distortion or the blur. You see here, look at this image and look at this image. There's a lot of blur, right? There's a lot of blur on this. If you increase the filter size, then the amount of blur will increase even further. And one more challenge here is that when you look at this image carefully, This image has some kind of boxiness. Okay, we'll have some kind of boxiness on that image. You'll have some kind of boxiness in this way because we are applying a filter which is also called as a box filter. If you have a filter with all same values, 1 1 1 1 1 1 in that way, this is called as nothing but a box filter. It's going to cause those boxiness, those boxes. Hence, to counter that, people have come up with another filter which is called as Gaussian filter. What happens in Gaussian filter is that you have this Gaussian curve. Gaussian is like normal distribution. At the central pixel, you'll have a very high value. And as and how you come down, the values will decrease. And if you come down further, the values will further decrease. Okay. If you're here, the value will be very less. As and how you come down, values will decrease. As and how you further come down, the values will further decrease. And as a rule of thumb, summation of all these values should be equal to 1. So just add all these numbers 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16. So you divide it by 16. And why are you doing that? Because all your filter values should sum up to 1. Hence we are doing that. So two filters is what we discussed. One is called as your box filter, which is also called as a mean filter or average filter. And if you keep increasing the size of your filter, the amount of blur or distortion in your image will keep on increasing. And the disadvantage here is that you will have certain boxiness, box shapes. To counter that, we started looking at Gaussian filter. In Gaussian filter, what happens? The values which are at the center will have high values. The immediate neighbors will have slightly less values, and the values which are far apart will be having less values. So if you keep going down this contour, the values will keep decreasing. The weightage keeps decreasing. And when you apply a Gaussian filter, you'll have a blur. You have a blur here. Okay. If you increase the size of the Gaussian, this is a Gaussian that you have. If you increase the size of the Gaussian, increasing the size of the Gaussian means you increase the width or variation. If you have a Gaussian like this, it will have some variation. This variation is called as sigma. If the variation is going to be large, then the sigma value will be large. The larger the sigma value, more will be the amount of blur. If the sigma value is 2, blur will be less. If the sigma value is more, blur will be more. The amount of blurriness. Look at this. This, if you apply your panda images like this, if you increase the sigma value, the amount of blur increases. If you increase your sigma value further, amount of blur further increases. So in short, you have mean filter or box filter. And if you increase size of filter, then amount of blur increases. Okay. When will the amount of blur increase? When you use a Gaussian filter. Let me ask that question. Whole question coming your way. If the sigma value increases in Gaussian filter, then the amount of blur will answer this, increase or decrease. Yep. Please, can you respond? Absolutely. You guys got it right in saying that. If the amount of blur increases, if sigma value increases, the amount of blur increases. Friends, one more thing quickly, I will take this poll. Um, because the attendance is dropping when we check with our participants, faculty, they were saying that they have some correction work and the colleges have started off, they are hardly finding any time. So will changing the timing from maybe 4 to 7, 4 p.m. to 7 p.m. increase the participation count? Yes or a no? What do you think? I request you all to respond. Let's see. Hmm. It is a 50-50% balance. What do I do? Let me capture the image here. Hmm. So roughly 48% of y'all say no. 51% of y'all say no, and remaining people say yes. Just wondering on how do we counter this? All right, let's see how it goes. Okay. Um, sure. So we will decide. We will decide and let you know. But I think we have to take a cautious call on this. All right. One more way to increase the amount of blur when it comes to Gaussian filter is that if you let your sigma remain as is, and if you increase your kernel size, even then the amount of blur would increase. If the sigma value is as is, and if you increase the kernel size, the amount of blur would increase. Okay. And all the values of smoothing filters should be positive, number one. Number two, when you add them up, they have to sum up to 1. And the amount of smoothing is proportional to the mask size. Mask or filter or kernel all mean the same. Okay, filter or kernel or mask all mean the same. So let's proceed further. Please answer this. If I take an image, that's the image of Edward Einstein. If you take image of someone basically, and if I apply that filter, what do you think will be the output? Please answer. What do you think will happen if I apply that? Okay. So you have this filter, you have an image, you're applying this filter on this image. And when you do that, what do you think will be the output? It will be exactly the same. Why? Let's see. Say you have an image, you apply this on this portion. When you apply it on this portion, what happens? 0 into this will be 0. This pixel into 0 will be 0. This pixel into 0 will be 0. This pixel into 0 will be 0. Only the central pixel value will get multiplied by 1. And then this central pixel value will be here. That central pixel will be this central pixel. That's it. So bordering pixels or the neighbor pixels will all be 0 because you are multiplying with 0. The central pixel is getting multiplied with 1. That means the same number. If this number is going to be 200, you multiply it with 100 and you'll get same 200. The same 200 will go here. Okay, then move it 1 pixel at a time. So you move it here. Once again, you will have the image and you'll also move the patch here. So neighbor pixels, all these neighbor pixels will get multiplied by zeros, and only the central pixel here would get multiplied by 1. So the same value will go here. Throughout the image, keep on moving your filter, keep on moving your filter. The moment you complete the first row, you come to the second row, you'll again start here. Again move it 1 pixel, 1 pixel, 1 pixel at a time. In that way, keep taking the central pixel values, keep replacing it. Okay, so there won't be any change. Now answer this. If I apply this filter on the image, what do you think will happen? Let me see. I'll give you another minute to answer this. Okay. So here we go. When you apply this, your image will become blur. Why do you think your image is going to become blur is something that we need to understand. Let's see. If you take this portion of the image, okay, and if you take all these values and multiply with your pixel, what will happen to the resultant? Let's see. You take this value and multiply it with 1. So you'll get this number. If this is 200, you'll get 200 plus. You take this number, multiply with this, you get another number plus. You take this pixel and multiply with this, you get another number. You take this pixel, multiply with 1, this pixel, multiply with 1, this 1, this 1, this 1. So that means all these pixels would be considered, and then you take an average of all those numbers. And when you take an average, you are in some sense not looking at only the central pixel. If I were to cut only this portion here, you're not just taking this portion, you're also looking at all the neighboring pixels and you're taking average of all those. So this pixel would get replaced by the average. So all these neighboring pixels will influence this. That would be this value. If you keep doing that, your image will look like this. It'll look very blur. Okay. Now this correlation and like similar to correlation, whatever we have done until now, we are taking an image and we are correlating. Like you have addition, right? And you have subtraction, you have division, and you have multiplication. In that way, you have another operation called as correlation. This is also called as cross correlation. Like you have addition, subtraction, division, and multiplication, you have another operation called as cross correlation. And that is what we are doing here. We are taking the filter and we are doing a cross correlation on the image. Okay, we are taking a filter, we are doing a cross correlation on the image to get the output. Okay, and on similar lines, we have another operation called as convolution. There is an operation called as convolution operation. Forget about the math part of it. Yeah, don't worry. Now let us understand about something called as boundary effects. This is very important. So if I take a, say, 5 by 5 image, okay, I'm taking a 5 by 5 image. All these things we will do it in OpenCV. Okay, we'll practically take an image and apply all these kind of filters and see what kind of responses we get. So you take the input image and then you apply a filter. Say the size of the filter that you're trying to apply is a 3 by 3 filter. You're applying a 3 by 3 filter on a 5 by 5 image. When you do this, we need to look at what will be the size of the output image. So you take this filter, and if you apply this filter here, and then when you solve it, let's see what happens. This into this plus 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 this into this uh, into this plus this into this. When you do that, you'd get the value of the central pixel, right? You go replace it. But then if I were to apply this filter on this portion, on this portion, come on. Okay, on this portion, then you don't have any pixel values here. That falls outside the boundary of your image, right? Since it's falling outside the boundary of your image, you cannot apply this filter on this patch. And only if you apply this filter on this pink color patch that you're seeing, you can get the central pixel value. And only then you can replace here. But you don't have it, so you cannot apply. On similar lines, you cannot apply this here and get this. You cannot do that because you don't have pixel values here. This effect is called as boundary effect, and hence when you get an output image here, when you apply this filter, output image size will become 3 by 3 because okay, when you apply it here on this patch, you get the central pixel, which is going to be this. Then when you shift this like this, you'll get this central pixel. That will be this. When you move this here, then you'll get the central pixel. You cannot move it any further. You cannot move it like this. Why? Because you don't have these pixel values. So you cannot move. So you cannot get these border pixel values here. Then you take this patch and you apply it on this, and then you get the central pixel. Then you apply it here. Then you get the central pixel value. Then you move it like this. Then you get the central pixel value. Okay. Then you move it downwards like this. Then you take the central pixel. Then you move it like this. Then you get this pixel. Okay. Then you move it again like this. Then you get the central pixel. Ultimately, you're getting all these pixel values. Okay, so the size will be so much and the borders won't come. And to counter this, people came up with a lot of techniques, and one such, or there are a few techniques that we're going to discuss. These techniques of dealing with your boundary effect is called as padding. What do you mean by padding? You just surround your image with additional pixels. Okay, whatever pixels are missed out, what did we say? That if you take a 5 by 5 image and if you apply a 3 by 3 filter on that, the output will become 3 by 3. So when I say boundary effect or padding, all you're saying is, since this is 5 by 5, in order to make this output 5 by 5, you need to add border pixels. Okay, you can add 1 pixel on. When you add 1 pixel and surround this image with the 1 pixels, and if you do zero padding means you know that pixel values range from 0 to 255. 0 means black, 255 means white. So you're replacing these borders with 0. Okay, and when you replace it with 0 pixels, if you add 1 pixel here and another pixel here, so you're adding effectively 2 pixels to the length. Already you have 3, you're adding 1 and 1, so it becomes 5. For height also, you're adding 1 pixel here and 1 pixel here, 2, and you have 3 here. So 3 plus 2 will become 5. So you get a 5 by 5 filter. Then you also have a lot of other techniques such as wrapping. Wrapping means, say you have, let me choose a different color. Okay, say you have this image. You take the same image and place it here. Okay, and cut it here. Take the same image, put it here. Take the same image, place it here, place it here, place it here, and here, and here, and here. Then what do? You just cut it there and take only this portion. This is called as wrapping. Then you also have something called as clamping. Clamping means, see, this is your image basically, that's your image. So what you're doing is you're taking this last pixel, you're repeating that last pixel throughout. You're taking this last pixel, repeating it throughout, last pixel, repeating it throughout in this area. Take that last pixel and repeat that last pixel throughout to get the size of the image. Again, if your image is 5 by 5 and if you apply a 3 by 3 filter, you get 3 by 3, right? In order to get 5 by 5, you are doing these things. There is another thing called as mirroring. Mirroring means whatever pixels are left out here, you take a mirror and replace it. Take a mirror and replace. Take a mirror and replace. Okay, take a mirror and replace. Replace the mirrors. This becomes an image. Okay, you can also blur the image and then do the required changes. This is how you deal with the boundaries. Okay, now another thing, and then we will take a break. Just pay attention here. If you have an image and if you're applying a filter, what will happen if you, this will ensure that you take a patch, all these bordering pixels, neighboring pixels will get multiplied by zeros. Only this central pixel will get multiplied by 2. So you are, in some sense, if you have say 30, if you multiply it with 2, it becomes 60. And you know that 0 means black and 255 means white. So you're going to take these by adding or by multiplying the pixel values, you're going to take these pixel values to a towards white. Okay, you're going to take those pixel values towards white. That is what this filter would do. And the next filter that you have here will blur the image. Okay, we have already seen this. You multiply each pixel values with 1 and take an average of that. It would blur the image. You are making the image bright and subtracting the blur from it. When you make your image bright, when you apply this filter on this, on your image, it makes your image bright. And when you apply this filter on your image, it will make your image blur. When you subtract the blur from your brightness, you get a sharpening filter. Your image looks sharp. In this way, you can use combination of various filters and do whatever operations you want. If you look at Adobe Photoshop, or if you look at Corel Draw, okay, or you look at Picasso, you look at Microsoft Paint, right? All of these things do exactly the same. Simple. You can go apply for a job in Adobe. Yeah, they do all these things. So if you take an image, if you first brighten the image and subtract the blur from it, it becomes sharp. It looks very sharp. The image looks very sharp, right? And the same thing can be done here also. You take your image, you smoothen your image, or you apply a blur on the image in some sense. When you subtract those two, you get to find only the details, like only those edges, if you observe there. Hey, focus on the concept, guys, not on this picture. Okay. And then if you take your original image and if you add some factor to this edges, image which has edges, you get your image which is sharpened. The point that I'm trying to drive is when you apply various combination of filters, you get a different result altogether. This is what you're expected to do. Okay. Now it's break time, 12:32. Let us be back by 12:42. Break time, please. So I think we should get started now. Uh, so let me erase this. And let us discuss about something called as template matching. All right. Template matching means you just take your filter. This template would be called as a filter or a mask or a kernel. You know, right, already? But let me recap. Filter or kernel or mask all mean the same. And you're going to use this and convolve it. Convolve or correlation, right? Like addition, subtraction, multiplication, deletion, you have cross correlation and convolution. You convolve this image throughout, and wherever you find an exact match, that is where you're going to have a bright spot. So there is an exact match of this with this, so you'll see a bright spot. Wherever you have a bright spot, that is where there is a match. This is called as template detection or template matching. The same thing I've told you, finding Waldo. This guy Waldo is lost in this clutter. Where is he? We don't know, right? If Waldo's parents go and complain to the person who is monitoring the beach and say that, do you know what? My kid is somewhere lost. We are unable to find. You have CCTV footages. Can you help me detect this guy? And trust me, if we have CCTVs everywhere, then no child kidnapping can happen. Even if it happens, just like that, cops can get hold of the people who are kidnapping the kids. It's so very easy, right? It's all about having the intent. And since I am from IIT, I can tell you that government has approached IIT already for such an application. Okay, so in railway stations, especially where people try to, kidnap the kids, very, very sad story. But then we can counter, let technology be used for the betterment of society as well, right? And they are, it is being used. It is being used in a big way. So what happens is you treat this Valdo as a template and you move this Valdo throughout your image. When you take this template and convolve it throughout, wherever you find an exact match, that is where you'll have this guy called Waldo. Let's see. Oops. Do you know where he is? Here. But it would be a tough task to detect Waldo. Hence, you make use of technology. And when you apply technology, the place or the point where you have, the place or the point where you have an exact match, that is a place where you'll have a bright spot. And quickly, the person monitoring the beach can say that, parents, don't worry, there you go, Waldo is there. That's it. That solves the problem. Right? It is just that you sit and then think about what kind of solutions make sense here. You can also use it for detecting vehicles. Here you have a template. Here you have a template of a car. And then if you convolve it, like addition, subtraction, multiplication, I'm saying convolve. Take this filter or template and convolve it here. And then wherever you find a similar kind of a vehicle, it says, yep, there is a match. This is how object detection works. Okay, so when will it work really well? When the scale, the size of this image, orientation, you cannot have a car in this way. I mean, the front of the vehicle is here and the back is here. If you have it in that way, then matching would be difficult. And if the general appearance is more or less the same, yep, it works well. Okay, that's about the images and how do you deal with your images. Now, a little bit of theory. Sorry, practicals. Let's do that. Here I have OpenCV. So let me open Spider and we will get into the practicals. For the remaining for the remaining, half an hour or so, whatever time we have, we are going to spend on programming. There will be approximately 1,000 lines of program which we will discuss, but slowly. We need not learn everything on one go, right? Slowly and steadily we will do it. Once again, one thing that I keep telling to the participants is that, friends, if you want to practice, okay, you need not have these files. I need not share with you the Python code as is. This is for lazy people who don't want to learn, who don't want to practice. For those people who want to learn and practice, watch the video, pause it, and type it. If you are not going to type these lines, you will not learn programming. Simple. And images, I would take whatever image I get from internet, doesn't matter. These are the images which I have downloaded just from internet. Okay, so you need not have exactly the same image. You can take any image from internet, and I highly recommend that you take your own image. You take your family images, images of your family members, of your kids, of your spouse, of your parents, and then start working. It'll be a lot fun, right? It'll be a lot of fun if you start using your own images here. That's one thing. And watch the video without fail and replicate it. When I say replicate, type it. If you do not put your fingers on your keyboard, there is no way absolutely that you learn anything. Okay, so that's a highly recommended thing. And that is what I've also instructed our team. I instructed our team to give you all access to data sets. Data sets are needed. Okay, the data sets that we have used in the past for running certain algorithms, those will be placed on our learning management system. We will place that. You might want to just download that. But the code, etc., we are not going to put on our learning management system because it's anyways there here recorded. And if you have access to the recorded video, that's the end of the story. How much ever you curse me today, after you watch the video and type it, you all will come back to me saying that, yes, this is the best way to learn. Right? You all as faculty members also give assignments to your students, right? It's exactly the same. If the student says, you gave me the assignment questions, give me the answer. Would you like it? No. It's similar to that. Okay. Take your images, take your parents' images, take your spouse, kids, relatives' images and work on it. All right. To get started, the first thing that you need to understand is that there is a library called as OpenCV. Okay, you have a library called as OpenCV. First of all, you need to check whether this OpenCV is installed on your computer or not. If it is not installed, you'll have to install it. And we now have OpenCV, a lot of versions available, but we would be making use of a specific version called 3. Right now, I think we also have OpenCV 4, which is available for our practice. So here it's extremely easy to install OpenCV. Let me first of all go to OpenCV forum directly and show you this. OpenCV 2. Okay. OpenCV is an open source. CV stands for computer vision. Okay. And it's used for various purposes. Various purposes. It's an open source basically. It is free for commercial use also, not just for your personal use, for commercial use also. And you can use OpenCV on Linux, Macintosh, Windows, iOS, Android, on all of these basically. Yep. And then one second, just let me make a note of this, that we have. Sorry, as of now I keep getting ideas. I keep making a note of that. From this website, I got some idea. Okay, let's look at the releases. The latest release is version 4. And we will also look into version 4. We believe that we need to be futuristic. And you know what? This was updated in April, and we are going to have it. As part of your training, we will learn version 3. Okay, how to install, how to use it, everything will be there here. You'll have resources, right? And the kind of craze that people have for this is exploding. Okay, so please explore this. Next, once you install the OpenCV, if you want to import that here, you just say import CV2. Okay, one second. All right. So when you want to install this, where is Anaconda? You go here, you do a drop down, you say here, you go and type pip install OpenCV-Python. In Anaconda, this is what you need to type to be able to install. Don't install any older versions. Let your Anaconda decide on which version is stable version currently, and say just install pip install OpenCV-Python. That's it. It will take care of the installation for you. Once you install it, you come back here and say import CV2. Then CV2.imread, image read. When I say IM, you're saying image read. And within the single quotes, you're giving the complete path along with the name of the image and the extension of the image. Your image can be .tif, JPEG, right? It can be in any other format, PNG format, any format will work. Okay, so you're reading the image, which is this mandrel. So let me go here and let me see whether that image is there or not. I need to check that first. Yep, we have the images. This is the mandrel image. I just downloaded from internet. Mandrel. That's it. So what I'm going to do now is I'll import it. So when you import the image, what happens is the moment you import, the image will appear in pixels. You have 256 by 256. That's the image size. Okay. And these 3 channels that you're seeing are red channel, green channel and blue channel, the three channels. Height and width of the image is so much, and you have taken all the pixels and you have listed it down here. Okay, you can choose your index value. You want index 1, okay, 2, 3, 4, in that way. All the 256, yeah, you will have all of those available. Then if you want to now view the image, you have to say cv2 dot image show. Im show means image show. What do you want to see? I want to see this image that has been, I want to see this image, and I also want to give the name of that window in which you are going to see the image as input image. So it will say input image, and you'll have the image here. Okay, and here you have another function called cv2 dot weight key of 0. These kind of things are called as flags. This is called as a flag in OpenCV. This is another flag. This is another flag. Flag is like code. What the number in this does is it takes a number which indicates milliseconds for rendering your image. What does that mean? For a specific duration, when you okay, let me run this and then show you. Maybe it might make sense. Say I type this, okay, and then you will find an image here, right? The name of this is input image. You have input image there, here, and the name of this window is also same. And this image that you have loaded, mandrill.tif, is appearing here. Okay. Now, how much time should you wait before you close this window? 0 milliseconds. If I say 100, you have to wait for 100 milliseconds before you close this window. That is what it means. And one more thing, very, very important. Click on this image, click on this image and press escape key. And your escape key has an ASCII character 27, meaning when you press 1, number 1 should appear. When you press 2, number 2 should appear on your computer. How does your computer understand? How does your operating system understand that if you type escape, it has to do a specific operation? For this, it looks at the ASCII characters, and 27 is a ASCII number. Okay, for escape key is 0. Then using image read, you're going to load the image, and you will see the image, and then wait key. Okay, now you have OpenCV, cv2.image read. You're giving your mandrill image, and you're saying cv2.image grayscale. This is called as a flag, right? All these, anything which you write after cv2 is called as a flag. So you want to load the image, and also you want to ensure that the image changes from color to a grayscale. So let me run this, and you're storing that in grayscale image. Now look at what has happened here. If you closely observe, you have a 3 here, you do not have it. 3 means it's a color image, red, green and blue, RGB. And here you do not have any, that means it is a grayscale image. Let us see that. To see that, you need to run these two lines together. cv2.imageRead. You want to view this gray image and you want the name of the window to be grayscale and weight key equal to 0. Okay, this is the grayscale image that we have. Press on escape and this is gone. Gone in the sense you can move on to the next line of code. Say you imported a color image and then you converted that to a grayscale image and now you want to save it onto your computer. To save onto your computer, you say cv2.imageWrite. If you want to read it, image read. If you want to write it, it is image write. So you're taking your image, which is this gray image, and you're saving it as output.tif. Let me run it. It says true. True means it got saved. Now you say import OS, operating system, and say os.get current working directory because you don't know where this file got saved. If you say os operating system dot get current working directory, you have it here. So I just go there and try to find on where did it get saved. C drive. I need to go to users and I'll go to Bharani Kumar and let me type it here. There we go, the output image. Output image is this manual image. Okay, then that's how you can write the images. Then once again, do you need to always give this import CV2? No, not needed. If you import it once, good enough. I'm just showing you because these are all different codes, different uh, actions which happen, right? Then import CV2. You're importing the image, which is your manual image, and then you want to write back your image. This image, you want to take that and you want to save it as output.png. So you have TIF, you're converting that to PNG format and you're using a flag image write underscore PNG compression, meaning you want to compress the size of the image. It doesn't work well because TIF is already a compressed format. You can take any of the JPG images if you want to experiment, right? You take a JPG image or JPEG, then apply this compression PNG, it will do wonders. It will reduce the size of your image. Okay, so this is also another thing that you might want to do. And this is called as a flag. Within OpenCV, all these arguments are called as flags. This is a flag in image write. Okay, and you have a lot of color spaces. Okay, for example, you have something called as RGB, which is red, green, and blue. And then we have something called as CMYK. You have something called as YUV and HSV. All these are various color formats. We will look at those color formats here. RGB is going to take a weighted combination of red color, green color, and blue color, and it is going to give you different other colors. And each channel, once again, red channel has values in the range of 0 to 255. Green also will be in the range of 0 to 255. And blue also will be in the range of 0 to 255. And I can go here and then quickly show you. RGB. We'll have subtractive formats, additive formats. I'll show you here. This is additive color mixing, meaning you take a project all these red, blue, and green on a white surface. Take a white color background and you project your colors onto that. And when different colors mix, look at that. You're getting pink color. I think this is magenta. This is yellow, green. Green, red, and blue are the basic colors. When you keep changing the intensity of these colors, you keep getting different other colors. And these are used in your CRTs, old TV. We used to have television sets, old television sets here. By the way, I still use old television set, okay? Or your old computer monitor. We have then LCDs, plasma, right? OLEDs, then quantum dots, so on and so forth. You have another model called a subtractive model, which is called a CMYK. Here, what you do is you take different colors, again mix and a match, and project it against probably a black surface. And you keep getting different colors. In your printers, you have your color printers. In your printers, you usually use that. Okay. So, yep. So in this way, there are a lot of other color combinations. You also have something called as YUV color space. Let us understand this also. RGB is good, but it is very limited when it comes to your real world applications. So people thought, you know what, in a color, in an image, it's not just color features that are important. The intensity information is also important. Then your statisticians, your computer vision experts sat down and they thought, how do we crack it? And then they came up with something called as YUV, wherein they told Y stands for luminance. I'm sure you know that light intensity is measured using luminance, right? Or intensity. And then this U and V, these color channels are used for color information. This works in various applications, okay? Because human, you and me, for example, we perceive intensity values differently than the color information. So it's very close to how humans think and how the human visual system works. Then again, it turned out to be that YUV wasn't helping in a few other applications. Then again, your computer vision experts sat down, they have done research. That's what you do, right? As PhD scholars, you take from where the research was left and you take it further. And you come up with some groundbreaking, ground shaking, inventions. Here, H stands for hue. Okay, and then these are all different properties of a color image. You can just search it. Saturation, S stands for. V stands for value. Hue, saturation, and value. This is a cylindrical system where we try to separate three of the most primary properties of your color. And you represent each of these as different color channels. This is extremely close to how a human visual system understands color. Okay, this gives us a lot of flexibility to deal with your images. And you can do this. You can say import CV CV2, and then you can say print all those values which start with color underscore, and whatever is available in the CV2 directory, display those. Okay, that all these are the combinations. You can you can convert some color called as Bayer to BGR. Different color formats to different color formats is what you can do. Let's see. Okay, say you're reading an image, this mandrel image. By default, if your image is color image, it will get imported as color. By default, if your image is black and white or grayscale, it will get imported as grayscale. Right? But here we are explicitly giving another flag called as image color. Even if you don't give that, it doesn't matter, of course, but then still. Once you import this, you can use this function cv2 dot convert the color, which is an image format, this image, and convert this image color, which is in RGB format, red, green, and blue. In which format do you want to convert that to? Grayscale. You want to convert that to a grayscale. Done. You have a gray image. Then you're saying cv2.image show. Take this grayscale image and convert that to a gray image. Okay, run it. Oops, I should have run this also. I didn't do that. My bad. That's why it's showing here like this. Now it will not let me quit. So where is that? Where is that? Here it is. Yeah. Okay. Usually you run those two together. Okay, not separately. All right. Now what we are doing is I'm saying, okay, take this image that you have imported, convert the color. This time, take the image and convert it into from BGR, that is blue, green, red. However, RGB or BGR doesn't matter, to YUV format. You want that to be converted to a YUV format. Once you convert the image to a YUV format, you're now saying, let me split all the three channels, Y channel, U channel, and V channel. I want to split those, and I want to view all those three splits. So you run it and you run this. So we are going to see the Y channel, U channel, and V channel separately. There we go. Okay, so you have this color image which is converted to Y, U, and V, and then this is your Y channel, U channel, V channel, Y channel, U channel, V channel. In that you have Y. In U channel image you have U. In the V channel you have V. Look at that. It's more or less looking like a grayscale. Yeah, there's no big difference. Also, I can split the image into green, blue, and red, and then I can show you how a green channel, blue channel, and red channel will look like. I'll get to this part later, okay? Let me skip that part. This is your green channel. This is your blue channel. This is your red channel. So what are we trying to do now? I'm going to read the image and I'm going to read it in color format. Even if you don't give this flag, it doesn't matter. It will load. Then you are taking that image and splitting the image into green, blue, and red. And then you're saying cv2.image, green, blue, and red channel. And I run it. Where is this red channel? Where is the blue channel? And where is the green channel? Here we go. What did I say? Even if you have a color image, if you split it into the three different channels, you'll get red, blue, and green. Okay, so this is how it is. So next week, we will quickly have this quiz, right? Quiz competition, etc. Enoch, are you there?
Yeah, Bernie.
Wonderful. So in the next 5 minutes, you'll have to run that quiz. So you might be ready. In the
Yeah.
next 2 minutes, rather. Okay, I'll just wind it up. So here we have red, blue, and green channels. All these three channels look like a grayscale only, right? I just press escape and job done. Okay. So all these things that we have discussed would come up in our mind map today. So please have access to this mind map and keep reading this. Okay, this is one thing. Okay, next thing is, uh, yeah, that's okay. Let's not fight, please. Okay, I've just seen your message. Sorry. Yeah. So we have, all right. It was slight diversion for me. Sorry. So please make best use of the mind map, number one. And on the weekend, we are going to upload the data set on our learning management system. Okay. From our team, we will do that. There are only very small files, that's fine. But from practicing this OpenCV, I would strongly recommend that you watch the video on our YouTube and just type it. Only if you type, you will learn. Simple, right? And yeah, we want you all to learn at the end of the day. All right. So over to you. Thank you all so much. Hope our team was explaining or answering to your queries. And yep, Enoch, you might want to take it further.
All right, Bernie. Thank you. So, yesterday we did post quiz questions on both LinkedIn and Facebook, and a lot of you responded. And what we had done is we had collected all the names of the people who participated in the quiz. And yesterday we had about 248 people participate in it. So, we are going to pick one random person and we are going to give a surprise gift. So I guess now all of you will be able to see my screen, and you can see that there is 248 people who have participated. So let's do this. I'm gonna type in random number generator, and we can see I could go from serial number 1 till serial number 248. So minimum is 1 and the maximum is 248. So the moment I click on this generate button, a random number would be generated here, and that whatever is the name corresponding to that number, that person will get the lucky prize. So let's do this. 3, 2, 1, and go. So today's lucky winner is number 132. That would be Sandeep BN. Sandeep BN, congratulations. Our team will get in touch with you and will give you the details on how you can access your gift. And congratulations once again, everyone who had participated, and Sandeep BN. And I look forward to seeing you guys tomorrow. Congratulations again.
Not tomorrow. Tomorrow we don't have. Once again, we are going to connect on Monday and take it further.
All right. Sorry,
Yeah, yeah.
Monday.
Yep,
Over
sure.
to you, Bernie.
Yep, thank you all so much. On Monday, we will connect and take this discussion further. Thank you all. Your code will run on any version, latest of the versions of OpenCV, Mary. Okay. Yeah. Yeah. If you have responded, your name would be there, Abhishek. No problem. All right. Thank you all. Bye. And not bye. Sorry. Uh, we will take your questions if you have any. Enoch, in the interim, you can just post the links here, the quiz part or the YouTube video.
Sure, Bante. I'll
Yeah,
do
yeah,
that.
you can do that because we still have time, 8 minutes. So, and we can also respond to the queries of our participants in the interim. Yeah.